So that system is one system, or to represent the orientation of one image. But however, there is the other the other system to describe the orientation of a certain image, which is the TSA, the tilt, swing, and azimuth. So I put some translation of the, well, you can say the Chinese name of the Chinese term over here. Tilt is 倾角, swing is 摆角, azimuth is the 方位角. Right, so, and let's take a look over here. So the TSA, so here, of course, the L is the perspective center, and then you have the image plane over here, and here is the ground, and ground and data. Okay. So the first thing is that you can identify the optical axis, which is over here. So you can say this is just a line from the perspective center, and draw a perpendicular line to the image, and then that line is the optical axis, which in Chinese is called 光轴 optical axis. Optical 就是光学的意思，光轴，光轴。Or you can just call it is the camera axis, where the camera is looking at. So that's the axis of that. And then beside that, you can also draw it's a vertical line. So you can draw a vertical line from the perspective center. And we already defined that if you draw a vertical line, then that vertical line will may intersect with your image. Then that point is called image nadir point. 相抵点 image nadir point. And if this vertical line intersect with the data, then it's called data nadir point. If intersect with the ground, it's called ground nadir point. So basically, that's the vertical line from your perspective center. Okay. So and then as you can see, this vertical line and also your camera axis and also your perspective center, it can form one certain plane, right? One certain plane, and this plane has a specific term, which is called principal plane, So this, you can say, basically this indicated area over here. And in Chinese, the principal plane is called 主纵面. Okay. Okay. So, and the other thing is this principal plane will intersect with the image. And for example, this is the line that it intersects. And this line also has a specific term, which is called principal line. Right? So the principal line in Chinese is called 主纵线. Alright, so and in this case, we can start defining what is the tilt, swing, and azimuth angles. So the first one, let's take a look at the tilt. Tilt angle is, right, so here, maybe you can see it better from a longer distance. So here is a small t. So this indicates the tilt angle. Okay. So if you have vertical photo, so as you can imagine, if you have a vertical photo, then your optical axis will be exactly the same as the vertical axis, vertical line. So in this case, the tilt angle is 0. But however, with the tilt photo, of course, your optical axis and your vertical line will have an angle, and that is called tilt angle. And tilt angle is called 倾角. Okay, should be easy to understand. Okay, so then the other thing, let's define what's the swing angle. So as you can see, the swing angle is over here. So here we have the on the image plane we have the principal line, and then so if you start from the y-axis, so on the image we also have a coordinate system. So we have the x-axis and y-axis. The swing angle is the starting from the y-axis and draw the clockwise. And go clockwise to the principal plane. Clockwise and to the principal plane, or to the principal line over here. So in this case, this angle over here is a small s over here. That is the swing angle. Right? Swing angle is over here. And the last one, azimuth. Azimuth is what people know, should already know that. So the azimuth is the 方位角. So which means that you can start from the north, and then go to your principal plane. right? So here is the north direction, and of course you draw it from the vertical line. So you can start from the vertical line and then start from the vertical line and pointing at the north, and then go clockwise to the principal plane. Then this angle is the azimuth angle. It's the azimuth. Okay, so you can use the TSA, tilt, swing, and azimuth to represent the orientation of one single image. Okay. Any question on this part? Any question? Okay, so if no question, and actually, to be honest, for the photogrammetry, this system, TSA system, is not so important. It's not so important. The reason I talk about this is because, as you can imagine, we have two systems of to represent the orientations. The TSA actually is good in terms of the graphical view. So when you draw, for example, when you draw the image and like that, draw illustration like this, then the tilt, swing, and azimuth is easy to help you to identify what's the orientation of that image. But however, the omega phi kappa is not so easy. So omega phi kappa is not so easy for the graphical representation. But the omega phi kappa is good at the mathematical calculation. It's good at the mathematical calculation. So what I mean by that is, we talked about this before, so I don't want to do that again. So the omega phi kappa system is that we have three axes. We need to define the x, y, and z axis first. The x-axis is the flight direction. So this is your flight direction. And the z-axis is the opposite direction of the vertical line, right? So that's the z-axis. And the y-axis is from your right-hand theory. So that's your palm direction. So you have your x, y, and z axis. And in this case, the omega phi kappa, omega is the rotation angle along the x-axis, right? You have the x-axis over here. So the omega is the rotation angle along the x-axis. And phi is the rotation angle along your y-axis, so which indicates this. And kappa is the rotation angle along your your z-axis, so which is this. Right? So omega, phi, kappa. Okay. So that's the representation or that's the omega phi kappa system. And it's not easy, as you can imagine. It's actually, if you ask someone, if you tell someone, say, okay, so right now my image plane is like with omega phi kappa orientation, then you ask him or her to draw that, draw illustration of that, then it will be very difficult. But however, the omega phi kappa is good at the mathematical calculation. So what does I mean by that is, as you can see here, is if we can assume one system, which is the x-plane, z-plane, x-plane, y-plane, and z-plane. So as you can see, we have the x-plane, y-plane, z-plane. And that x-plane, y-plane, z-plane is the axis that you can say parallel to the object space. So in the object space, we also have the x, y, and z coordinate system. Right? We also have the x, y, and z coordinate system. And then the x-plane, y-plane, z-plane, that's the coordinate system in the image space. But however, that x-plane, y-plane, z-plane is parallel to the object space x-plane, y-plane, into the object space x and y, z, x, y, z system. And let me repeat it again. So in the object space, you have the large x, y, z system. And then for the, maybe I'll draw it. Alright, so for example, alright, sorry. So you have the x, y, and z axis for your object space coordinate system, and so you can define a certain coordinate system that is parallel to the object space coordinate system. Right? That is what you assume. One coordinate system that parallel to the object space coordinates. And if your perspective center is over here, then which indicates that here is your perspective center and here is your image plane. Right. So if you have this as your perspective center, and in this case, if also your omega phi kappa is 0, right, omega phi kappa is 0, then which means that it is a vertical photon. It is a vertical photon. Okay. So and basically that's the case. So, but however, in reality, of course, every time when we take the photo, take the image and take the photo, it has a certain orientation angles. So in this case, first which means that we need to understand the coordinate transformation between these like perfect vertical coordinate systems with the tilt coordinate systems. So which means that maybe we have another axis like this. Maybe in reality, let me try to draw it. Maybe in reality, this is our tilt photo coordinate system. And we want to understand the coordinate transformation equation between this tilted coordinate system with this vertical photo coordinate system. So that's what we want to do right now. Okay, so we want to understand the relationship between x plane, y plane, z plane coordinate system with the x, y, z coordinate system. Right, so that's what we want to understand right now. Okay, so any question till now? Any part you guys don't understand? Okay, good. So let's move on. So in this case, as you can see, first, if we define the x plane, y plane, and z plane coordinate systems, and then in this case, the omega is along this x plane. And the other thing that you guys want to may need to notice is that the omega phi kappa, the direction of counterclockwise, is positive, right? The counterclockwise is positive, right? So which indicates that if this is the x-axis, and if you have, for example, 45 degree of the omega, then you need to rotate to the counterclockwise direction. And here is the, you can say, here is the omega for 45 degree, right? And the same thing goes to the phi. If you also have the 45 degree of the phi, then the counterclockwise direction, that is the that is the angle, okay? And yeah, basically that's the case. All right, so in this case, let's first assume this is the x plane, y plane, and z plane. And then first, and actually to understand the relationship between the x plane, y plane, and z plane with the final x, y, and z, actually we will do it step by step. And actually the steps are omega first, phi the second, and kappa the last. Okay, so we will rotate omega first. So as you can see here, the dashed one, the image plane, that is the x1 and y1 and z1, which indicates that the coordinate system after you rotate the omega. Right, that's the coordinate system after you rotate the omega. Okay, so as you can see, it's rotated, and then here, as you can see, the other thing is, if you have the three axes, originally this is x plane, y plane, and z plane, and the new one is x plane, x1, y1, and z1. So as you can see, one thing, there's among these three axes, there's one axis that doesn't change if you rotate omega, which is what? Omega, which is what? X-axis, right? So the x-axis is x1 and x1 because you are rotating along the x-axis. So the coordinates of the x-axis coordinates doesn't change. So only the y and z coordinate they change. Okay. So in this case, you can simplify it to become a two-dimensional, say, y-axis and z-axis, a two-dimensional rotation. So it becomes a two-dimensional rotation. Should be very easy. So in this case, let's take a quick look over here. For example, here, supposedly, originally we have the x, y, z, and right now, x is this direction. X is this direction. So you have the x and y is over here, and z is over here. So because you are rotating along the x-axis, so this coordinate doesn't change. So you only need to consider these two axes and the rotation of it. So it will be the y plane and z plane to the y1 and z1. Alright, so it will be a rotation from this axis, this coordinates system to this coordinate system. So, and this should be very easy. You are the relationship between the y1 and z1 with the y plane and z plane is like this. You are just it's just a two-dimensional coordinates transformation like this. It's just a rotation. Okay. So I won't explain that. You guys should understand that directly. And after that,